Good afternoon, xtUML Days attendees. My name is Levi Starrett. Today I'm planning on speaking to you a little bit about persistent Shlaer-Mellor modeling. Before I do that, I want to take a moment to introduce myself. As I said, my name is Levi Starrett. I'm married and I have 5 wonderful kids. I graduated from Purdue with a bachelor's degree in computer science in 2016. From there, I spent 3 years working with Starrett as part of the OneFact team, where I mostly worked on Bridgepoint tooling. I did a little bit of model compiler work, some consulting, and even some training. In 2019, I transitioned into the industry. I worked for 2.5 years for an ag technology startup company called Rogo. There we did autonomous soil sampling for fertility management. I was the software architect there, and I brought modeling into our team in a couple different ways. All the way from the embedded architecture, where we used Bridgepoint and MC3020 to generate C for Atmel microcontrollers, up to the web application side of things, where we generated JavaScript classes from an object model and used them to populate a database. This summer I transitioned out of that job and started working full-time for my own private company, Brooklyn LLC, where I do consulting and other xtUML related work. My passion there is really in model compiler development. I'm the original author of the Sierra model compiler and continue to be working on that project today. So before we get too deep into it, I want to define a few terms so that we all know what we're talking about when we're talking about persistence. I did look to see if there was a good definition of persistence in the existing literature. I had my research team on it, but he didn't find anything.
Oh, other views.
So I decided to come up with my own definition. I did look at some other sources and kind of combine them to come up with my own words to define what persistence is. Persistence is the characteristic of a system in which the state of a system continues to be maintained even after the life of the process which created it. A couple other characteristics of a persistent system, or capabilities of a persistent system, is writing to non-volatile storage. So typically the state is maintained through some storage mechanism which isn't dependent on the memory of the system. This allows future executions to just pick up where it left off in the previous execution. Sometimes we use pre-populated instance populations to give the system a warm start. We'll talk about that a little bit later. And we can save snapshots of the system state and do what we want with them. So when designing a persistent architecture for a model-based system, the first thing you have to think about is data locale. Where is the data going to be stored? Sometimes this can be done in some sort of database system. It can also be done in a local file system or a virtual file system. For example, the Bridgepoint xtUML editor uses a file-based system to store and persist the model data that represents the metamodel instances for a project. I did work with a project that was in the web and used a document database called IndexedDB backed by virtual file system to store instances that way. Other examples would be the Mazel model compiler, which uses SQLite and backs their data with local files. The next major decision you need to make is exactly what data you need to be persisted. Not every system persists everything, but certain parts of the state. For example, attributes can be persisted, and they can be selectively persisted. Links between instances and associations can be persisted. The current state of each instance can be persisted, as well as in-flight timers, events, and messages coming from outside the system. These can be defined in different ways, but sometimes marking is used to determine which parts of a system are persistent and which parts aren't. A package can be marked as persistent or not, a class can be marked as persistent or not, or even attributes within a class. I'm curious if any of you have done work with persistence and how you have solve the problem of deciding what elements are persisted and where in your application they're persisted. Once you know where you're going to persist the data and what data you're going to persist, you need to decide when you're going to persist that data. There are a variety of strategies that have been employed in this section, and I'm going to just touch on a few of them. The first one I want to talk about is the load and dump method. This would be where you start up your system, and at the very beginning you load all of the instances in your population from persistent storage into memory. You operate on them in memory as the application runs. You may create new instances, modify attribute values, add associations, or delete them. And then at the end of the application, before exit, you dump the instance population back to persistent storage. One of the advantages of this strategy is that it's very simple. It avoids performance penalties due to unnecessary persisting and loading of instances. It is not robust, however, to unexpected shutdowns, as if the system shuts down before the instances are dumped or when the instances are in an inconsistent state, it can cause a lot of data loss. An example of an application that uses this type of persistence strategy are model compilers such as the Sierra model compiler and MC3020 model compilers, which load the instance populations produced by Bridgepoint, operate on them, and then either dump them for later use or completely disregard them. Another strategy used for persistence is the Writethrough method. In this strategy, the backing mechanism is used directly for every instance access. So for example, if you were using a file-backed system, every time an instance value was accessed, you'd be accessing the file. And anytime an attribute value was updated or an instance association was created or destroyed, the files would be updated. This method is also very, very simple, which gives it an advantage. However, it struggles with performance issues because the file system, or what other mechanism you're using for your persistence, is required for every instance access. It's also robust against data loss because every instance update is persisted right away. Instances can also be persisted periodically. In this strategy, a time component is involved. For example, an instance population may be serialized every 500 milliseconds. This avoids some of the underlying performance issues of the write-through method and provides a little bit better data consistency than the load and dump method, where dumping only occurs one time, and it doesn't have to add the additional complexity of a transaction-based system. This type of system can also be further optimized to prevent persisting during idle periods, so it can be very efficient. One example of this type of system in use is the web application that I helped build for Rogo. In that system, there was a bit that would be marked dirty as soon as the instance population was changed. If the dirty bit had been set for more than 500 milliseconds, an instance population serialization event would occur. If the bit continued to be set, the timer continued to be extended. So as long as you were writing instances, it would wait. And then as soon as you were quiet, it would serialize the population, and it would check every so often. A final architectural strategy for persistence is the transaction method. If you know databases, this will be familiar to you. In a transaction-based system, the changes or deltas that happen to the instance population are collected throughout the length of a transaction. When the transaction is complete, all of those deltas are combined and serialized to the instance population. This allows it to be very high performance and also not wait too long to persist. When you're building a transaction-based system, you need to decide what your transaction boundaries are. For xtUML or Shlaer-Mellor, a good option for this is the thread of control. The thread of control starts when an external event, such as a signal or a timer, starts an activity going. The thread of control ends once all of the events generated by that activity and subsequently generated by those following activities are handled. One feature of a transaction-based system is that it gives you the ability to roll back transactions if there's a failure. For example, if there's an exception during the thread of control, you can choose whether or not to commit the transaction or to abort it and give an error back to the user. We've talked about persistence mechanisms provided by the architecture, but persistence can also be exposed to the user in the application through bridge operations. MC3020 provides an interface through an EE for non-volatile storage and persistence. The save state bridge was also created to take binary snapshots.
Cheese.
Not that type of snapshot. To take snapshots of the system at a given time for them to be interpreted later. I alluded earlier in this presentation to using pre-existing instance data to provide an application with a warm start. What I mean by this is having instances created before the application starts which provide initial conditions for the system. Often this is static or semi-static instance data. Consider the following example of the class diagram that represents a user access system. Highlighted in blue are the task class, permission, role, and user. These instances are configured by the administrators of the system and don't change very often. They're loaded as pre-existing instances and then used and queried to log in and provide sessions for a user. Oftentimes, these pre-existing instance populations can be very large and even at times more complicated than the application itself. Here, tasks and roles are related together using instances of permissions. To create a new user, the system administrator would need to create a pre-existing instance of the user class. To add a permission to that user, he would create an instance of the permission class and relate it to the appropriate role and task class for the user. You may start to see that sometimes it's good to have an application dedicated specifically to generating this pre-existing instance data, which then can be persisted and loaded by another application used for the business logic. If you've used pre-existing instance data in an application before, use the chat now to tell your story. A great example of a complex application of pre-existing instances using persistence is Cooper Security. Cooper built intrusion detection systems for residential and commercial properties. These systems were often more complex to configure than they were to actually run. The configuration involved creating rooms, adjacency between the rooms, policies for the rooms, and different things like that. The actual security systems were built on very simple hardware, 8-bit microcontrollers and small EEPROMs for persistent storage. The configuration application, however, was robust and built to be run on a PC. These applications work together with the same class population, where the configuration application could be used to create an instance population and persist it, and then that persistent data could be transferred to the target architecture and used as pre-existing instance data for the runtime application. Another example that I've mentioned about persistence in the real world is the Bridgepoint model editor. Although Bridgepoint doesn't operate with a full Shlaer-Mellor runtime, most of the classes within Bridgepoint and the metamodel itself are actually generated using an xtUML model compiler. Bridgepoint uses a transaction-based approach backed by the file system. Each top-level model element, like a package, a component, a class, and all of their sub-elements, make up a single file on disk. The transactions are kept in memory until the transaction is complete, at which time the files are persisted. Only the files which receive changes are persisted. This makes things better for things like version control management. Transactions are also very important to manage the undo-redo stack for the Bridgepoint editor. MC3020 provides a Statesaved bridge that was developed for Worldview a few years back. This bridge is intended to provide low bandwidth communication of state for remote monitoring. Worldview builds high altitude observation balloons that do a variety of things such as weather observation, aerial photography, and such. They required a way to monitor the state of a system from afar with a very low bandwidth communication. Because of this, the Statesaved bridge generates a binary representation of the state and the attribute values and sends it over a network. The state can then be reinterpreted by an application on the client side where an engineer can inspect the state. In addition to supporting loading Bridgepoint instances for model compilers, MC3020 provides a couple application-level interfaces for persistence. As you can see from the class diagram, this is a modeled persistence mechanism where links and instances are modeled as classes. Non-volatile storage is modeled as a catalog where items can be retrieved and persisted by ID. The application can go through the persistence EE, which uses the non-volatile storage EE to provide the persistence mechanism. They can also use the non-volatile storage for persistence directly. The Mazel C++ model compiler and software architecture may be the most complete example of a persistent architecture publicly available today. The Mazel architecture uses a transaction-based approach, where each thread of control is concluded by committing a transaction to the database. This transaction contains all of the updated instances from the thread of control. If an exception occurs during the thread of control, the transaction is not committed. Because of this, the Mazel architecture allows us to be very robust about maintaining model integrity. If there's a model integrity violation which causes an exception, or some other exception in the system which prevents the thread of control from completing, it assures that instances that are corrupt are not persisted to the model. The Sierra model compiler employs a very simple load and dump instance population persistence mechanism used for developing model compilers. This mechanism allows the model compiler to load instances from Bridgepoint, do transformations to a separate target model, and dump the instances along with new created instances from the target model. In addition, an AWS DynamoDB persistence mechanism was created, which was a combination load and dump and transaction based. The instances were all loaded when the system started up, but deltas were maintained and only the changed instances were updated. This system was designed to start completely from scratch on every thread of control. So when a signal or a timer would come in, the application would start up, load the instance population, execute until all of the events were handled, persist the updates, and then shut down. This would happen over and over and over as the application ran. It was intended as a proof of concept of an architecture that could run on serverless web services like AWS Lambda or Google Cloud Functions. I am currently working on extending the Sierra model compiler to support a transaction-based approach to persistence. This approach will be able to support crash recovery, meaning no data is corrupted or lost if an exception is encountered during execution. System start-stop, meaning the system can be brought down safely and restarted without any loss of data. And concurrent ready, meaning that multiple instances of the application can be running in separate processes and still be able to execute concurrently without corrupting any data. This can be done by mapping classes onto existing database frameworks and using locking mechanisms to prevent data from being corrupted when accessed from multiple different sources at the same time. The long-term vision for this project is to build a Shlaer-Mellor architecture which could be run on cloud service providers such as AWS, Google Cloud Platform, or Microsoft Azure. Execution could be done on serverless code execution platforms such as Lambda and Google Cloud Functions. The persistence of the instance population could be done in managed services such as Amazon RDS. Events could be routed through managed services such as API Gateway or others, or use external mechanisms for routing. This type of strategy would be very good for scalable, long-running applications that are low-rate applications. It would not be a good fit for real-time or very high-rate applications. I hope I've given you plenty to think about with regard to persistence in Shlaer-Mellor models. I'd love to hear your questions in the chat as we go forward. Okay, go.
How did